Welcome back, YouTube. This is Dave Lucas with Injection Molding Skills and More. Today we're going to go over a troubleshooter and a scientific troubleshooter, what the differences are, and then go over the documentation and stuff. So I got a video inside of this video. The guy really details it, really simplifies it more than I could do it, in a better way than I could do it. So I want you guys to follow along. I hope you guys enjoy the video. Again, this is going to go over troubleshooter versus a scientific troubleshooter, okay? So I hope you guys enjoy this.
Let's define who is a troubleshooter. According to Merriam-Webster, a skilled worker employed to locate trouble and make repairs in machinery and technical equipment. As we compare a typical troubleshooter to a scientific troubleshooter, you'll note that a typical troubleshooter will act upon learned behavior, will rarely document anything, and will avoid speaking in specifics. Now let's define science. According to Merriam-Webster Dictionary, this is the state of knowing, knowledge as distinguished from ignorance or misunderstanding. So what is a scientific troubleshooter? Scientific troubleshooter combines both science and troubleshooter and results in a skilled worker who acts from a state of knowing. Let's talk about how a scientific troubleshooter acts. The scientific troubleshooter will know the history of the process, mold, machine, material, and technology, determine what's changed, will act on knowledge, and will verify the results of any change. A scientific troubleshooter relies on process documentation. So now, as a scientific troubleshooter, let's look at machine inputs versus process outputs. As you can see from our little animation, inputs are the parameters and conditions fed into the process. Outputs represent data and information that can be obtained from the process. As we get into the discussion about the importance of process documentation, you'll note that setup technicians most often document machine-dependent settings or parameters, such as injection speed or transfer position. A scientific troubleshooter will document machine-independent outputs, such as temperature, times, plastics pressures, weights, and any additional data that's relevant to the process. Please be sure that you take note of this important difference between a setup tech and a scientific troubleshooter. In the next few slides, I will give you some more examples of what you may want to take note of. As an example of a process output, let's talk about temperature. You should always record the actual plastic melt temperature along with the coolant temperature in and out of the mold. Another example that a scientific troubleshooter looks for specifically are items such as fill time, pack time, hold time, gate seal time, cycle time, and recovery time. When looking at process outputs for pressure, always record the actual pressure applied to the plastic. Please note that a scientific troubleshooter always focuses on machine-independent parameters such as plastic pressure, rather than hydraulic pressure, which is machine-specific. Always ensure that you document the weight of the part. This documentation should take place after fill, after packing, and after the hold is complete. You should always conduct a part weight study to determine when gate seal actually takes place. This will ensure that you're using the appropriate hold time. Every molder and process has specific information recorded. For example, things like cavity measurements, quality measurements, clamp tonnage, photographs, any kind of observations, and how the cavities are balanced. To reiterate, the scientific troubleshooter uses documentation to know how the process ran, determine exactly what changed, act on knowledge, and verify the results. The typical troubleshooter usually asks, what buttons do I push to correct the defect? This is exactly what we're trying to point out to you, is not to get into this type of a habit where a typical troubleshooter will often rely on learned behavior or troubleshooting guides. This is why you hear documentation stressed throughout this presentation. People claim that documentation is important, but they just don't get around to doing it. You'll see in the following examples why good documentation can help you easily identify the source of the problem. First, we're going to talk about flash. When looking at a defect, we want to determine what has changed from our documented standard. So in this case, if flash was a result of a high melt temperature or degraded polymer, you would most likely see a drop in plastic pressure at transfer from fill to pack. And you'd also see a rise in overall part weight. If the melt temperature were low, causing flash around the runner or center of the mold, you'd also see a rise in pressure at transfer and a drop in the overall part weight. If the flash was due to a high injection rate, you'd see an increase in part weight and pressure at transfer. Also, you'd note a shortened fill time. If the flash you were seeing was due to a low transfer set point, you would almost see identical symptoms, but you'd find an increase in the fill time rather than a decrease. If the flash was due to a high pack pressure and hold pressure, your fill weight would be the same, but the pack weight and final weight would increase. Although this is one of the first things people change when troubleshooting flash, in most cases, increasing clamp tonnage is used as a band-aid. In all likelihood, something else in the process has changed. If you're running a multi-cavity mold, you can often see a high imbalance where some cavities flash, while others intermittently short, and the fill time will vary. If this is the case, you may want to consider evaluating the cavity balance of the tool during filling. If the check ring is running inconsistently, you might have a tough time maintaining a constant fill, resulting in intermittent shorts and flash. This would be easily identified in a shot-to-shot change in part weight during fill. If your mold or platen was deflecting, your process outputs would change little, as with a low clamp pressure. The big difference here is that deflection and flash is the most likely to occur in the center of the mold. If mold damage and wear happen to be the culprit, then you'd see flash in a particular spot in the mold. This would come up repeatedly. And this defect is most often the cause of when you're getting flash in a short shot. In this case, we'll discuss both sinks and voids together, since most of their causes tend to be the same. If your defect was a result of a high melt temperature, then the polymer can shrink excessively, causing sinks and voids virtually anywhere on the part. Aside from an increase in melt temperature, you're most likely to see an increase in the fill-only part weight, as well as a drop in the pressure at transfer. Unlike the high melt temperature, low temperature polymer increases the pressure loss in the mold, and this often results in sinks or voids near the end of fill. In this case, you'll often see an increase in pressure at transfer and a lower part weight during fill. As with a lower melt temperature, a low injection rate can also cause high pressure losses, again resulting in sinks or voids near the end of fill. But a drop in pressure at transfer will also occur. If the transfer point is set too high, too little material will enter the mold during fill, and this will result in shrinkage near the end of fill. In this case, you would see a drop in both pressure at transfer and the part weight during fill. Too often, pack and hold pressures are increased to correct for sinks and voids. You should first verify that filling related outputs such as fill weight, pressure at transfer, and melt temperature are the same before adjusting these pressures. If you see a sink or void near the gate, it's typically the result of insufficient hold time. When the mold temperature is too high, excessive shrinkage will occur anywhere in the part. This is especially true with semi-crystalline polymers whose crystallinity increases when the rate of cooling is reduced. These are plastics like nylon, acetal, as by way of example. In such a process, you may see little change in the process except for a rise in the pressure at transfer. In a case unique to voids, a low temperature mold can cause the polymer to freeze to the mold surface. As a result, most of the shrinkage takes place internally, causing the polymer to pull away from itself, creating voids. To many molders and their customers, short shots can be one of the most frustrating and costly defects. When you have a low mold temperature, too much pressure loss can occur during fill, and this results in an increase in transfer pressure and a drop in all of the part weights. As with a low mold temperature, low injection rate increases the pressure losses in the mold. In this case, the pressure at transfer should decrease. When the transfer set point is too high, you will see a drop in pressure at transfer as well as all of the part weights. In most molding processes, the packing phase should be used to fill the last few percent of the mold cavity. If the packing pressure happens to be set too low, the fill-only part weight will not change, but the part weights after pack and hold will decrease. Jetting or worming is a unique defect that occurs when a stream of material shoots into the mold at the start of fill rather than creating a smooth flow front. A low melt temperature increases the material's viscosity. This viscosity can prevent the material from creating a smooth fountain flow as it enters the mold. In this kind of example, you should observe an increase in pressure at transfer and a drop in the fill-only part weight. A high injection rate can prevent the polymer from creating a proper flow through the gate. If this is the case, you should see an increase in transfer pressure and fill-only part weight. And you'll also notice a drop in fill time. Lastly, jetting will occur if the mold temperature is too low. If this is the case, you'll see little change to the process except for an increase in the pressure at transfer. As you can see, if the process is documented, the scientific troubleshooter can quickly identify what has changed. In this section, we'll cover the typical steps or methodology to scientific troubleshooting. Step 1, examine the part and make sure that your diagnosis is correct. Step 2, although we stress a scientific approach to troubleshooting, you should always investigate the simply obvious cases, or causes, I should say. For instance, if you have splay, check the material and the dryer to make sure that it is adequately dried. That's one example. Compare the current process with the documented process. Without proper documentation, troubleshooting can only guess what has changed. Make the changes necessary to correct the defect and return the process back to the standard. Once the defect is corrected, verify that your process is running to the standard. This helps prevent other defects from occurring in the future. Document the changes that were made so that there is a record. In conclusion, it's not only about troubleshooting a process. All factors such as material, mold, machine, part design, and technology must be documented.
Okay, I hope you guys enjoyed that video. I hope you guys learned a lot of stuff out of that. I guess please like, share, and subscribe. It really helps the channel out. The more views I get, it helps everybody out. Give a thumbs up. I really do appreciate all the support to the channel. It helps me out. It helps others out that are out there in the molding industry. So please like, share, and subscribe. Till next time. Woo, yeah.